Pause for a second. Right now, somewhere in Italy, there is a harbor that has been sitting underwater for over 2,000 years. Not crumbling, not dissolving, not breaking apart. Just sitting there, perfectly intact, getting stronger every single decade that passes. The concrete holding that harbor together was poured before Jesus Christ was born, before the Roman Empire reached its peak, before anyone had ever heard of Portland cement, or steel reinforcement, or any of the materials we use to build our world today. And here is the part that should make your jaw drop. The concrete we pour today, the concrete holding up your roads, your bridges, your skyscrapers, starts degrading within 50 years. 50 years versus 2,000 years. So the question you need to ask yourself is this: what exactly did we lose, and who decided we were never going to find out? Stay with me, because what I am about to show you does not just rewrite the history of construction. It rewrites the history of human intelligence itself. My name is not important right now. What is important is that you pay attention to what comes next, because most people go through their entire lives without ever knowing this story, and the people who do know it tend to not talk about it very loudly. Before we talk about what the Romans figured out, you need to understand what we use today, because the contrast is genuinely shocking. Modern concrete is made primarily from something called Portland cement. Portland cement was developed in the early 1800s. It works by mixing limestone, clay, and other materials, heating them to extreme temperatures in a kiln, and grinding the result into a fine powder. When you mix that powder with water and aggregate, that is sand and gravel, you get a chemical reaction that hardens into what we call concrete. It is strong, it is fast to produce, it is relatively cheap. And it has one major, catastrophic flaw. Portland cement concrete reacts badly to seawater. When salt water gets into modern concrete, which it always does because concrete is porous, the chloride ions attack the steel reinforcement bars inside. The steel rusts. When steel rusts, it expands. When it expands inside concrete, it cracks the concrete from the inside out. This is called spalling. You have definitely seen it. That crumbling, flacking concrete on old bridges, old walls, old buildings, that is spalling. That is modern concrete dying from the inside. The average lifespan of a modern concrete structure, 50 to 100 years with maintenance, often less in marine environments. We have buildings in major coastal cities right now that engineers are already planning to demolish and replace. They are barely 30 years old. Now hold that thought. We have been taught a very specific version of history. The version where ancient people were primitive, where they were smart enough to survive, but not smart enough to build anything that truly lasted. Where progress is a straight line that goes from grunting cavemen to the modern world, and everything before the Industrial Revolution was basically just people stumbling around in the dark. That version of history is wrong. It is not just incomplete, it is not just missing a few details, it is fundamentally, demonstrably, provably wrong. And the proof is not hiding in some controversial fringe theory. It is not buried under classified government document. It is sitting at the bottom of the Mediterranean Sea, in plain sight, being studied by some of the most prestigious scientists at some of the most respected institutions in the world. The proof is Roman concrete. And once you understand what Roman concrete actually is, what it actually does, you will never look at ancient history the same way again. Before we talk about what the Romans figured out, you need to understand what we use today, because the contrast is genuinely shocking. Modern concrete is made primarily from something called Portland cement. Portland cement was developed in the early 1800s. It works by mixing limestone, clay, and other materials, heating them to extreme temperatures in a kiln, and grinding the result into a fine powder. When you mix that powder with water and aggregate, that is sand and gravel, you get a chemical reaction that hardens into what we call concrete. It is strong, it is fast to produce, it is relatively cheap. And it has one major, catastrophic flaw. Portland cement concrete reacts badly to seawater. When salt water gets into modern concrete, which it always does because concrete is porous, the chloride ions attack the steel reinforcement bars inside. The steel rusts. When steel rusts, it expands. When it expands inside concrete, it cracks the concrete from the inside out. This is called spalling. You have definitely seen it. That crumbling, flacking concrete on old bridges, old walls, old buildings, that is spalling. That is modern concrete dying from the inside. The average lifespan of a modern concrete structure, 50 to 100 years with maintenance, often less in marine environments. We have buildings in major coastal cities right now that engineers are already planning to demolish and replace. They are barely 30 years old. Now hold that thought. The Romans built their harbors and piers and breakwaters using something completely different. They called their material opus cementitium, and it was not made with anything you would recognize from a modern construction site. Roman concrete was made from three primary ingredients. First, volcanic ash, specifically ash from the region of Pozzuoli near the Bay of Naples. This ash is called pozzolana, and it has been used since ancient times in the region. The Romans noticed, through observation and experimentation, without any of our modern chemistry, that this particular ash had remarkable properties when mixed with water. Second, seawater, not fresh water, actual salt water from the ocean. And third, chunks of volcanic rock called tuff, along with pieces of brick and rubite. Now here is where it gets extraordinary. When Roman builders poured this mixture into wooden forms in the ocean to create harbor structures, something happened that they could not have fully understood, but clearly recognized as valuable. A chemical reaction began. The seawater reacted with the volcanic ash, and as that reaction proceeded, it did not stop the way Portland cement does. It kept going, slowly, over years, over decades, over centuries. The reaction created new mineral structures inside the concrete, interlocking crystals of a mineral called aluminous tobamorite. These crystals grew into the spaces and microcracks in the concrete, filling them and reinforcing the structure from within. The seawater was not destroying the concrete. The seawater was literally making it stronger. Scientists at the UC Berkeley National Laboratory, which is one of the United States Department of Energy's premier research institutions, published a landmark study on exactly this process, and their conclusion was stunning. After 2,000 years of constant exposure to seawater, Roman marine concrete was not weaker than the day it was poured. It was stronger. Let me say that again. 2,000 years of saltwater immersion, and the concrete was getting better. The ocean itself was feeding the concrete, helping it grow, hardening it in ways that modern materials science is only now beginning to understand. This is not theoretical. These structures exist. You can go see them. Caesarea Maritima, on the coast of modern-day Israel, this was one of the largest harbor complexes in the ancient world, built by Herod the Great under Roman influence around 20 years before the Common Era. Parts of this harbor are still visible today, some above water, some below. Portus Aeolius, near Pozzuoli in Italy, ancient naval base now partially submerged, still structurally sound. The harbor at Cosa, on the Tyrrhenian coast of Italy. Roman concrete structures here have been directly sampled and analyzed by researchers from UC Berkeley, Harvard, and institutions across Europe. And at every single one of these sites, the same finding emerges. The concrete is not just surviving, it is mineralogically active. It is still changing, still strengthening. Meanwhile, the Eisenhower Interstate Highway System, the largest infrastructure project in American history, begun in the 1950s, has required constant, multi-billion-dollar repair and maintenance. Some sections have already been fully rebuilt twice. A Roman harbor built by hand, with volcanic ash and seawater and no machinery, is still standing. Our highways, built with cranes and computers, and the full force of modern industry, need to be replaced within a generation. Something is deeply, fundamentally wrong with that picture. Now, here is the question everyone asks at this point, and it is a fair one. If Roman concrete is so superior, if it is stronger, longer lasting, and more resistant to the most corrosive environment on Earth, why are we not using it? Why did this knowledge disappear for nearly 1,500 years? Why, when it was rediscovered, did it not immediately replace Portland cement? There are several layers to this answer, and I want to be honest with you about all of them, because this is where the story gets complicated. The first layer is genuinely historical. When the Roman Empire collapsed in the West in the 5th century, the institutional knowledge that sustained large-scale Roman construction did not survive in written form accessible to medieval builders. The formulas, the sourcing of specific volcanic ash, the mixing ratios, these were largely lost. Not hidden, not stolen. Lost, the same way countless other pieces of ancient knowledge were lost in the chaos of civilizational collapse. Medieval builders reverted to simpler materials they understood, and those simpler materials became the standard. And then, when the Industrial Revolution demanded mass production of construction material, Portland cement emerged as the answer, not because it was better, but because it was scalable. You could make it anywhere. You did not need specific volcanic ash from specific locations in Italy. That is the innocent explanation. But there is a second layer, and this one is harder to dismiss. The pozzolanic principle, the idea that volcanic ash mixed with lime and water produces an extraordinarily durable binder, has been known in scientific literature since the 1800s. The Romans wrote about it. Vitruvius, the Roman architect and engineer, described pozzolana in his work De Architectura, written around 15 BC. This was not hidden knowledge. It has been sitting in libraries for centuries. And yet the construction industry, a multi-trillion-dollar global industry with enormous financial incentives tied to the current model, the Portland cement model, did not pursue it. Research into Roman concrete specifically, the deep materials science investigation into why and how it works, only really began gaining momentum in the 2000s. Serious papers were not published until 2013. Major findings were not widely circulated until 2017 and beyond. For a discovery this significant, that is an extraordinarily slow adoption of knowledge. Who benefits from the status quo? Cement companies, construction conglomerates, infrastructure maintenance contracts. The current model is not just a technical standard. It is a financial ecosystem worth hundreds of billions of dollars per year. Every road that crumbles needs to be repaved. Every bridge that degrades needs to be rebuilt. Every coastal structure that spalls needs replacement. If your concrete lasts 2,000 years, you only sell it once. I am not telling you what to think about that. I am just telling you to think about it, because Roman concrete is not the only example, not even close. Let me give you two more briefly, because each one deepens the picture. The Iron Pillar of Delhi. Standing in the Quip complex in New Delhi, India, is a solid iron pillar approximately 7 meters tall, weighing over 6 metric tons. It was forged sometime around the 4th or 5th century of the Common Era, roughly 1600 years ago. It has been standing in the open air, exposed to rain, humidity, and the elements of northern India for all of those 1600 years. It has not rusted. Not significantly, not in the way that modern iron or steel rusts when left outside for a decade. The corrosion is minimal, superficial, and has essentially stopped progressing. Metallurgists from institutions including the Indian Institute of Technology studied the pillar extensively. Their finding, the iron contains an unusually high phosphorus content, which creates a thin protective layer on the surface called mesawite, a compound that actually prevents further oxidation. The ancient Indian metalworkers who forged this pillar, somehow, whether by accident or by deliberate knowledge, produced iron with exactly the right chemical composition to resist rusting indefinitely. Modern metallurgy only identified this mechanism in 2003. The pillar was forged approximately 1600 years before we understood why it worked. And one more. The Antikythera mechanism. In 1901, sponge divers off the Greek island of Antikythera recovered a corroded lump of bronze from a shipwreck dated to around 60 to 70 BC. For decades, nobody knew what it was. It looked like a rock with some gears inside. Then, in the 1970s, using early imaging technology, researchers began to understand what they were looking at. And the understanding has only deepened since, with advanced X-ray tomography revealing the full complexity of the device. The Antikythera mechanism is a mechanical computer. It uses over 30 interlocking bronze gears to predict astronomical events, solar and lunar eclipses, the positions of planets, the timing of the Olympic Games. It models the irregular orbit of the Moon. It accounts for the Metonic cycle, the Saros cycle, and the Callipic cycle, astronomical periods that require sophisticated mathematical understanding to calculate. It was built 2,000 years before the first known mechanical clock appeared in medieval Europe. The mathematics required to design this device, the gear ratios, the compound mechanisms, were not supposed to exist in the ancient world. This level of precision engineering was not supposed to be possible before the Industrial Revolution. And yet there it is, sitting in the National Archaeological Museum in Athens, real, physical, undeniable. We did not build anything as mechanically complex as the Antikythera mechanism in the Western world until the 14th century, and when we did build it, we thought we were inventing something new. We were not inventing it, we were reinventing it, badly and more than 1,000 years late. So what does all of this mean? It means the story we have been told about human progress is wrong. Not slightly adjusted, not missing a few footnotes. Wrong in its fundamental premise. The premise is that ancient people were limited, that without our technology, without our science, without our institutions, humans in the past were operating at a lower level of intelligence, of sophistication, of capability. The Roman concrete, the Delhi pillar, the Antikythera mechanism, and dozens of other examples we have not even touched today, they prove something different. They prove that human intelligence has not changed, that the minds who walked the earth 2,000 years ago were as capable of observation, of experimentation, of discovery as any mind alive today. They were working with different tools. They had different information. They faced different constraints. But they were not lesser. In some cases, they were better, not because they were superhuman, but because they were solving problems with focus and longevity that our system simply does not reward. Roman builders were not trying to build something that would last until the next infrastructure bill. They were building for eternity. That is a different mindset, and it produced different results. We replaced that mindset with a mindset of efficiency, of production, of scalability. And in doing so, we did not just move forward, we left things behind. Profound things, irreplaceable things, things we are only now beginning to recover if we are honest enough to admit they were lost in the first place. Now, to be fair, and this is important, the scientific community has not ignored this. Researchers are actively working to replicate and adapt Roman concrete for modern use. Marie Jackson at UC Berkeley, one of the lead scientists on Roman concrete research, has been instrumental in identifying the specific mineralogical processes at work. Her team has worked to understand not just what the Romans used, but how to apply those principles in contemporary construction, particularly in marine environments. There are pilot projects exploring pozzolanic concrete for coastal infrastructure. There is genuine momentum in the field. But it is slow, it is underfunded compared to the scale of the problem, and it is still fighting an entrenched industrial system that has no financial incentive to change. The knowledge is there, the science is confirmed. The results are sitting at the bottom of the Mediterranean Sea for anyone willing to go look. The question is whether the people who control our infrastructure are willing to use it, and whether we, the public, are willing to demand that they do. Subscribe. Watch next. The ancient Indian metal that scientists couldn't explain. Watch next. The Antikythera mechanism. Full story.